Okay, because of the your requirements, we will only revise the practical aspects of this first set of experiments. Okay, the list of experiments that you have conducted in the first cycle, as I said that single phase AC circuits in which you have the necessary background, three phase AC circuits you have the necessary background, and single phase circuits you have more or less the required background. Maybe we will cover it, single phase transformer, and about the DC generator and DC motors. You know, the DC, these were one of the earliest type of machines. The DC generator is the one which is produced to generate DC voltage from a prime mover. Okay, so if you have a prime mover which drives this armature at a given speed, and the armature is in the it is rotating, so there is a stationary part where you have a field winding, okay, and through this you pass a DC current, and then as you pass a DC current, by this rotation it induces a voltage, okay, and this voltage is proportional to the speed and the flux. So for a given speed, so if you increase the and this flux is normally related to field current. Okay, if you increase the field current, the flux will increase. So if you increase the field current, flux will increase and the voltage will increase. But because it is not linear, as the magnetic core of the field winding gets saturated, so it goes to a nonlinear region. This is called the open circuit characteristics.
So what is the meaning of saturation of the core?
Yeah, saturation of this core, because of the core, magnetic core in the on which it is wound, it gets saturated. The flux is not directly proportional to the field current.
So what is the meaning of saturation here, sir?
What is the meaning of saturation? It was done when what is BH loop? That is magnetic saturation. I think it was explained several times that after if you exciting BH, whatever after a certain flux in a core, the additional flux you must put much larger exciting current. Okay, that is called magnetic saturation. Okay. It was said that, okay, if people are coming into the room, if the room is empty, it requires much less effort to get into the room. But if the room is very much crowded, the next man coming in has to put more force to barge in. Like even a crowded bus. If bus is empty, you just walk in. But if the bus is full, you become more pressure to get in. Okay? So for an additional person to get in, you may require more pressure. Same thing is here. Okay? And therefore, you have this type of a characteristics. And all you have to do is to observe what is the effect of the field current and what is the effect of speed. You obviously expect if you change the speed for different values of speed, you get a different characteristic based on this relation. This is one thing which you are observing in the laboratory. Okay, it is related to the field current. Of course, we will do this more in theory in subsequent lectures. But just to give you a background to what you have done in the laboratory. Next is about the for the same generator, if you connect a load, then as that means if you connect an electrical load, the more current will be drawn. As the current is drawn, it is observed that the voltage at the load will go on decreasing because of certain drop in the internal circuits. So usually this is what is observed. As you increase the load, the voltage drops down. I mean, it happens in any electrical system. Whenever the increase in load is there, because of internal circuit resistances here, it will what are these details, etc., we will do in the theory lectures, okay, later. So these are the characteristics which you are supposed to observe in the experiment on characteristics of a DC generator. Of course, there are also, this field current can be given by an external source, or it can even be connected to the same source, in which it becomes self-excited. So in order that either it is separately excited or self-excited, you normally connect the field winding mostly across the armature, which is called shunt excited. Okay, and in that case, to start with, you require some residual magnetism, and because of residual magnetism, there will be some small current will induce a voltage, and because of that voltage, there will be more current and so on. So it will come to some type of a stable operating region, decided by the resistance of the field circuit. Okay. Again, those details because of limitation of time we can't cover much. Okay. Next is about a DC motor. The last experiments which you did on DC motor, in DC motor what you do is you try to run it as a motor from a DC source. Okay, and I think you are trying to look at the how the motor speed changes with certain parameters. Okay, usually the speed is proportional to the voltage that is applied minus the internal resistance drops, and also inversely proportional to the flux. This is one of relation. Okay, in a normal such motors, again how we do it little detail later. So if you have this speed is proportional like this, so you can change the speed of a motor, DC motor, either by changing the voltage at the terminal or by having an external resistance in the circuit. Okay, add resistance in the circuit, or by decreasing the flux, because this is proportional to the field current. That is whatever current in the field. Either it can be done by external resistance here. Let us say this is armature resistance and this is the field resistance. Okay. Therefore, you are not loading the if you load the machine, again there will be some further change in speed, but for in this case you are just observed, is a preliminary observation how a motor works from an electrical energy to mechanical energy, and how that speed can be varied by these methods. Okay, so this is an experiment which you are doing in the laboratory. Okay. Yes. What is meant by rated speed? So there is what is meant by rating? That is okay. It's a good question. What is for example, this room has a capacity of say 60 students. So that becomes a rating. Okay, that's come capacity, a normal thing where everything works. Okay, if you put 100 students, means it is overloaded. If you put 10 students, it is underloaded. Okay, so everything has certain rating that way. Any motor is certain rating. It operates at 220 volts. That is a rated because it is designed according to that. It is designed to take that voltage and insulation, magnetic circuits, everything is designed accordingly. A current, a conductor, you say it is rated for 10 ampere motor. That means at 10 ampere, all the copper is optimally utilized. If you put 1 ampere, it is underutilized. If you put 20 amps, it will get overheated. Okay, so everything there is a rating. Okay.
So can we have speed below rated speed?
Yeah, you can have speed below or above rated speed. The thing is, after all, many things are sort of variable speed applications are there, like a ceiling fan, for example. Ceiling fan operates at different speeds. A machine tool will operate at different speeds, or a cassette tape recorder may operate at different speeds. Okay, there are applications. Maybe an electric vehicle operates at different speeds. So that speed variation is quite common. But there is what is known as a base speed or the rated speed, for which it is designed. Okay, but there are also applications where they always operate at rated speed. Okay, like a pump most probably. Okay, they normally operate at the nominal speed. Okay. So this is an experiment which you have already conducted. Okay, then I'll go to the other experiments which you have you will be doing in the coming period. Then you have one experiment on BH loop of magnetic material. Okay, and then other experiment I think is on AC generator. Another is an AC motor, 3-phase. And you have one on the DC series motor, and I think you have one on single phase induction motor. I think we have lined up about, if I remember correctly, about 5 experiments in the second cycle. Okay. I think we have, pardon? That is AC generator, is alternator. Okay. Do you think any other experiment is, or DC shunt motor is there? Characteristic of DC shunt motor? Or shunt motor? Okay. Okay, the first one, you have a magnetic core. A magnetic core, you would like to know the BH loop of this material. So you know, in a CRO, this is the X plates and these are the Y plates. If you can somehow make the X plates to have take a signal proportional to H and Y plates to take a signal proportional to B, then you can get a BH loop here. So in this experiment, what you are observing is, we have seen that if you put a small resistance here, this signal is proportional to I. Okay? And then if you take a small another, because you want some signal proportional to flux, so all you do is you take an integrate. You have an integrating circuit. So whenever the voltage here is integrated, it becomes flux. So you get a flux signal. So there is an integrating circuit there, typically an RC circuit, okay, which is used. So this experiment you are conducting, where you can monitor the current and monitor the flux. So you feed current across the x-axis and the flux across the y-axis, and since current is proportional to H and flux is proportional to B. Okay, so you get a BH curve in this. So you observe, and you will also see by changing the voltage levels, you can change the flux level, you can change the Bmax. So you can also get various BH curves for different Bmax. Okay, so you can have one below the inside the other. So, and you can also observe that the magnetizing current is having third harmonic. So if you plot I, so you can have I versus T or phi versus T, and you will observe always phi is always sinusoidal and I is always non-sinusoidal. Okay, whatever we have discussed in the theory lecture, you will observe it in this experiment. You can look at the BH loop of the material. Okay. As far as the next experiment, a AC generator. Here again you have a we have seen how three-phase AC is generated by having either by rotating the conductors in a magnetic field, or by rotating the magnetic field in a stationary conductor. Okay, so you get a three-phase output. Generated from an AC generator, okay, by having a, either you can either rotate the field, that means you rotate a field and put the conductor stationary, or you rotate the conductors and put the field stationary. It has a relative motion is there, and you can take out these voltages. So what you are observing is this voltage is AC, so the voltage RMS will be proportional to the, again proportional to this field current, okay, and voltage is proportional to the flux that is produced and also the speed, similar to DC. So you are asked to check up what will be the characteristics for different speeds. Again, this will be for N1, N2. For different speeds, you have a voltage generated. This experiment you are conducting, you will observe what is the voltage generated at different speeds for different field current. Okay, this is again a very simple experiment, this observation, I mean, you notice here it is RMS value of voltage that is generated. Okay, then you will also conduct, you can also repeat it for connected to a load. Just like a DC generator, this is an experiment on an AC generator, where you will observe that the voltage that is generated will also be, if this is the current drawn, this is all three phase, if the current drawn is, if you load it, then you would expect a drop here because of the internal impedances. Okay, so this is again another observation that you will do. So you will just do two experiments on this. So in all of the experiments, the prime mover is typically a variable speed DC motor, so that you can adjust the speed. And one precaution you take whenever you use a DC motor, you start with low voltage, so that there is no high starting currents. So those starter arrangements are there in the laboratory, so you can take care of this. This is the experiment on AC generator. Okay. Then there is a three-phase AC motor or induction motor. Okay, that is the next experiment. Okay, induction motor. It normally has, a stator has three-phase balanced windings, and rotor has short circuited windings. So what it broadly what it happens is, whenever you apply a three-phase voltage, we will show later in theory that it creates what is known as a rotating magnetic field in the air gap, because the currents are changing with time in three phases, and the windings are there, so it is as if you are spinning a magnet, okay, at constant speed. Whenever there is a magnetic field in the air gap rotating, in the rotor there is an induced current in the rotor because it is short circuited like a transformer. So the rotor tries to align with the stator field, so it will start catching up, so it rotates like that. Okay, this is one of the inventions of Tesla, and which was invented in 1886 or so, this three-phase induction motor. Okay, so this is the largest motors ever manufactured in the world, largest number, and it handles almost 80% of electricity produced in the world, these three-phase induction motors. And they are used in all workhorses in industries or induction motors. They already have the pumps, blowers, compressors. They are all mostly three-phase induction motors. And you are conducting an experiment in this case by applying to this one three-phase supply. Okay, and then you normally measure the speed, and in this case you are doing mostly a no load experiment. You will measure what is the you conduct two tests. One is called open circuit test, where you just don't load it and measure the input voltage, input current, input power, and from this you can calculate some of the internal parameters of the circuit by the formula which is given in the laboratory instruction sheet. And you also do conduct what is known as a short circuit test, where you basically operate two zero output tests. See, output of a motor is proportional to torque and speed, isn't it? In one case you put torque equal to 0, in the second case you put speed equal to 0. So in both cases it will give you the input power which goes mostly in the losses. In one case it goes into core losses, another case it goes into the copper losses. So in one test you are operating at nominal voltage, second test you are operating at reduced voltage, so that means second test you are operating at nominal current, first test at nominal voltage. Okay, by conducting these two tests you will have some information about the motor parameters and how it works. Because since there is no coupling arrangement with these motors, you can't do load test. But of course, if you couple it to some other loading system, a load test on this can also be conducted. Okay, this is about the third experiment on single three-phase induction motor. Okay. Okay, then you have again a single phase induction motor. One experiment where instead of three phase, it is similar to three phase motor, but stator has single phase. Because most of the single phase motors, small capacity motors, all used in domestic appliances like your refrigerators, the fans, your desert coolers, air conditioners, they are all single phase motors. So we thought it will be good if you conduct some experiments on this. So here again you are supplying only a single phase supply. Okay, and you measure what is the voltage, current, power under different. I think you can also have a loading here. You conduct at different loads, what will be the characteristics, how the speed, because output is basically speed and torque, input is voltage, current and power. So you will have some idea of the characteristics of a single phase motor, which are again used in large numbers. In fact, single phase induction motors are also the ones which are produced in millions. Okay, on this. So, okay, then you will have a characteristic of DC motor. These two, the experiments, DC series motor, DC shunt motor. So you have this experiment. In a DC motor, there are two ways of course, broadly two ways of connecting the field winding. Either they can be connected in series like this, armature and field, they are series, or they could be across. Is shunt, and supply is like this. Because we will understand it better when we go to the again further lectures. But in this the characteristics of these two are different. One is when you connect them in shunt, both of them you are loading it. Okay. Normally loading is done through another generator indirectly. Okay, so when your experiment will be basically what for a given voltage, you monitor the input power as you change the output power, and how you will also see what is the effect of speed on the load. Okay, and this experiment is important for two reasons. One is these series motors are used in several applications like electric trains. All the electric trains presently used in India use DC series motors, and they operate at very high starting torque, because in most of the trains the torque at starting is high because passengers are sitting in the train. Okay. Therefore, similarly are in drilling machines, where initially the torque at starting is high. Or even AC series motors are also used in all the food mixers, etc., domestic. Yes.
Do we use three-phase induction motor in the trains?
That is a recent trend. Recent trend is to have three-phase induction motors, because that is been now with electronic control that is possible. You can have a desired characteristic of a DC series motor. Okay. That's the recent trend is to go for a variable speed three-phase induction motors. So that's why it is expected that some of these motors may have a reduced applications. Okay. So shunt motors are normally constant speed motors. They have two different characteristics. Okay. Usually the motor characteristic is normally signified by the speed versus torque. What do you expect? If supposing this motor is operating at some speed here, okay, as you load it, what do you expect the speed to be? Speed would decrease. So normally the speed would decrease with as you increase the torque on the motor. So this is what you will observe in a DC shunt motor. But the same is not true in the case of this is for the shunt characteristics. But interestingly, DC series characteristic is different, because as you load the motor, the current will increase, so flux will also be affected. Here the flux is not affected because flux is decided by the voltage. The difference basically between these two is, here the flux is decided by the current, here the flux is decided by the voltage. Here the voltage is constant, so flux is constant. Here the voltage is constant, but the current is not constant. Therefore, it is a flux dependent one. As the flux increases, again the voltage will be altered internally. So it has internal characteristic. So normally the characteristic of a series will be typically like this. So that is, now this is a series characteristics. Now that means ideally when torque is 0, speed is infinity, or when speed is 0, torque is infinity. That is why they insist that in food mixers you must push something to start. Okay, normally you are not expected to start some of these food mixers, etc., with nothing in the jar. Okay, it has to. They have this type of characteristic, and they operate at different speeds. Okay, and if you change the voltage, the characteristics will also change. Okay, so these are, yes.
So where do we use the shunt motor?
Shunt motors are used, wherever you need a variable speed operation, you can control. This is highly controllable speed motor, because you can control the voltage, you can control the field current, you can control the speed. In the experiment you have done in the class, in the laboratory in the first cycle is on DC shunt motor. You know how the speed can be easily controlled. They are used in textile mills, they are used in steel mills, they are used in mining applications. Okay, wherever you require a very adjustable speed, DC shunt motors were very much used. Okay, so this is a quick overview of the background that you need for conducting the experiments. Okay, I hope that you will now have no difficulty in either conducting the experiment or answering questions asked on these experiments. Okay. But I would still request you to sort of, if any doubts are there are instructors in the class, and you can get those clarifications, whatever. Okay. Now, in the last lecture, we learned the following, didn't it? We said in an ideal transformer, you have V2 by V1 equal to N2 by N1, I2 by I1 is N1 by N2, and volt ampere at input side V1 I1 is same as a volt ampere output side V2 I2. So whatever you input you give, the same volt amperes will come out, and that means whatever power you give becomes same as the power input becomes power output, ideally. And then we said whatever is the input voltage is opposed by the induced voltage E1 here. Okay, V1 and E1 are opposing. Similarly, whatever is the output load voltage is whatever is the induced voltage, the secondary will just come across the load. So they are opposing each other, and this that means there is a current I1 and current I2. Ideally, this relation holds good. Okay, but in practice, what are the practical problems? We made some assumptions in the last class. Ideal. This is an ideal transformer. So in a practical transformer, these following four factors are relevant. Okay, in a practical transformer. Okay, that means the core is of finite permeability, so it requires a finite MMF. It is not zero MMF, what we had assumed. Okay. Next one is, we said there are losses in the core, like hysteresis and eddy current losses in the core are there, which we neglected in an ideal transformer. Okay, there are core losses here. Okay. Next is the windings in both stator and the primary and secondary, they are having their own resistances. Okay. Then you also know that there are leakage fluxes in the core, because we assume that all the flux is confined to the magnetic core, but which is not so. There are some fluxes which goes out of the magnetic core. They are called the leakage fluxes. Okay, so let us look at how each one of these are accounted for. Okay, so number one is finite MMF. There is a finite MMF required for the flux. So for the flux, a finite current, let us say IM, is drawn from the mains. A finite current IM is drawn, and this current is called, a magnetizing current. This is called a magnetizing current. This is drawn from the mains. Okay, so earlier our phasor diagram, we can say let's say V1, V2 produced by the same flux phi m, magnetizing. Okay, this is the flux vector, this is V1 and V2 vectors. Okay, and of course this was V1, same flux is producing V1 in the primary and V2 in secondary, proportional to the N1 and N2. Now we are saying here that this will cause a current IM is drawn from the mains. Okay, the current IM is drawn from the mains in addition to other things. Okay, so if we draw our we will write here. So I will draw the ideal transformer. N1, N2, and what we are now saying is you add another current is drawn from the mains. Okay, this current is drawn. Of course, this is I will now call I1 and let us say I1 dash or something. This is I2. Okay. That means this current is from the mains. You are drawing this current, but this. Okay.
So why is this I1 dash here?
Because this is the one which is compensating for I2. Okay. Or I can.
So where is IM going?
Where is?
IM going?
IM is drawn because there is a magnetizing current. That means I am representing by a reactance here. In addition to this is an ideal transformer.
The core.
This is an ideal transformer. Okay. This is an ideal transformer, which we had earlier. Now we are having another current.
IM means the core is drawing for that production.
Earlier we said, and this I1 dash N1 plus I2 dash N2 will still be 0, but additional MMF is now coming because of the IM. That is required for, that is the added MMF is giving to produce the flux. Okay, that compensation still takes place ideally, but additional MMF is required because it is not 0 MMF. Okay, we say this is how it is done. Okay, now the next is. Yeah.
So why is this I1 dash used? For what purpose is I1 dash used?
Because that is different than, supposing you say I1 is the current drawn from the mains, that minus IM will become I1 dash, isn't it?
In an ideal transformer.
In an ideal transformer, I1 dash and I1 are same, because IM is 0.
I1 dash or I1, what, in an ideal transformer, isn't that used to create the flux?
Yeah, but there is, because you don't require any current to create a flux if it is 0 MMF. Okay. Now this is basically I1 dash is basically to compensate for I2. Okay. Now the next point which you said is about core loss. Okay. The next point is how to take care of core loss. We know that certain current has to be core loss. That means a current. How does the supply from the source? It has to come from source only. Core loss also has to come from source. Hysteresis eddy current loss has to come from source. So again, a current has to be drawn from source. A current has to be drawn from source. Let us call this as IC, and this is called core loss current. Okay. Now this current, where will it be? In which direction it would be? Huh? It should come from the source, and it is a loss. So is it in phase with the V1 or it is out of phase with V1? Huh? Core loss. It is a loss which is a power basically. So therefore this IC is in phase with the, this is in phase with supply. Okay. So you will have a current drawn in phase with the supply. Okay. You have a current drawn in phase with the supply. Okay. And this sum of these currents you can call it as I naught or no load current. So what we are trying to say is, even if there is no load on the secondary, it will draw two currents. One is the magnetizing current, another is the core loss current. Okay, even if there is nothing on the secondary, even if you keep the secondary open circuited, this current will be drawn. So if you connect any transformer, you know many transformers are connected as first device in any electrical gadgets. If the gadget is on, even if the device is not working, it will still be drawing a current. That current is to take care of magnetizing the core as well as for the core loss. So this is the phenomenon that you will observe to take care of the core losses, which is hysteresis and eddy current losses. So typically you can say that if this is the V1, if this is V1, we can say the current drawn is I naught with one component which is in phase IC and another component which is out of phase is IM. Okay, and this is represented, core loss is represented by a resistance RC, and this is represented by a reactance, let us say JXM, and this is called a magnetizing reactance. And this is called the core loss resistance. And these two currents are drawn even on no load. Okay. So you will observe that in addition to this, you can draw a another resistance RC which will draw. Okay. So the total current that is drawn, IC and IM, this is IC and this is IM. Okay. So in effect what we are saying is there is an I naught that is drawn like this, IC and IM, that you are adding into this network. Okay. Now next is,
Excuse me, the captain if these are constant.
pardon?
I think IM would be constant if these are constant, sir.
Yeah, so long as V is constant, yes. Okay. What is the next point that we have to account for is the, what is third point? Winding resistances. So how do you account for winding resistances? So all you do is connect R1 and R2 in series with the circuit. Okay. with V1 and V2. That is primary and secondary circuits. Yes.
So that IC was due to the some finite resistance of the core.
IC is the current component such that V into IC gives the power.
So no, that IC flows in the coil or in the core, sir.
IC doesn't flow in the core, it flows in the coil. It is drawn from the supply. Whenever something is drawn from the supply, it doesn't go into the core. Okay, but that is to compensate for the losses in the core. Okay, for hysteresis eddy current. In fact, if you draw this, so what you are really trying to say is, if you have the voltage here, voltage waveform, you will have the current, you have the core loss current like this, and where will be the magnetizing current? So that will be out of phase. So ICIM will be like this. If this is the voltage, this is the in phase current and out of phase current as per this is concerned. Okay. So you can have the, in this circuit, you add a resistance here and add a resistance here. Okay, let us call this as R2 and R1. Okay, so you are now trying to make it more and more realistic. From an ideal one where you have a voltage E1 and voltage E2 and current I2, and in this case current I1 dash or something we say, because to differentiate between the current that is drawn. Yes.
So here then the equation will be V1 I1 dash will be equal to V2 I2 dash, V2 I2.
Which one? Yeah, E1 I1 dash equal to E2 I2. Now you will not have V2 here. I think now this will become E2 here. Okay, because E1, E2 are ideal. This is an ideal transformer. Okay, now we are going to make it more realistic to take into account these things. Okay, then there is another. So we have seen, we have added all this RC, then XM, okay, and so on. Now the last point is about leakage fluxes. So we'll quickly look at this. Now we have said that this is the mutual flux and there will be some leakage fluxes here. This is more symbolic. Phi leakage of the primary, that is produced by the current I1. Okay, whatever current that there is a phi m and there is a phi L1, and you can say that E1 that is induced will be N1 into d by dt of phi m plus phi L1, because there a total flux is one which is producing E1. Okay. Similarly, if you have the secondary winding, E2, and this also has some leakage fluxes. Let us say phi L2, this is the secondary leakage. So we define phi L1 is the primary leakage flux, and we also have phi L2 as secondary leakage flux. Okay. So you will notice that whenever the current is flowing either in primary or in secondary, it is not only contributes to the mutual flux in the core, but also to leakage flux which leaks outside the core. So that has to be accounted for. Okay. Now we can define this. E1 is equal to N1 d by dt of phi m into phi L1, and similarly E2 in the other side will be what? N2 d by dt of phi m plus phi L2. We assume that this is all the leakage fluxes are the ones which is cumulative, okay, of all this thing. So how do you account for this in our calculations? Pardon? So by putting a series reactance, because that means you are able to say that self reactance will consist of this. That means let us say VL1 or EL1 and let us say E1 and EM1 or whatever it is you may say. I am just trying to simplify this. So this one you write it as a leakage reactance XL1 and this is the mutual reactance XL. Okay? So you represent leakage by a reactance in series, because that is the one which is caused by the current in the respective windings. There is no leakage here due to this. This leakage flux is only due to its own current. Okay. So we have a situation where in addition to this you can represent this by its, let us say, JXL1 and here JXL2. Okay. So your total system now looks like this. Your total system looks that we have V1 input supply voltage and draws a current I1 from the mains. Okay. You have a V1 drawing a current I1 from the mains. Then there will also be some drop due to primary leakage flux caused by I1, and also a drop in the primary resistance again caused by I1. Now you will see this is called resistance and leakage reactance of the primary. R1 is called the primary resistance and XL1 is called the primary leakage reactance. Now remaining, whatever remaining is the one which is operating to the flux, and because of that flux there is certain current, further current has to be drawn to account for the core loss, and also another current to account for the magnetizing flux. So after giving these contributions, this I1 will now be will be changed to I1 dash. So obviously I1 dash will be equal to I1 minus I0. That is, this total current of this is this. And then you will also see that the E1 will be equal to V1 minus I1 into R1 plus JXL1.
One is EM.
Pardon?
So
Yeah, in a way, because that's just a, but the voltage, that is ideal voltage E1, which is, because to differentiate between EL1 and EM I have said that, but EM is basically the what is the ideal voltage in the core which is proportional to N1. Now, similarly, then E1 in an ideal transform get transformed to E2. Go to the secondary proportional to N1 and N2. And in the secondary again, whenever you load it, it draws a current, and therefore there is a drop across resistance and drop due to leakage reactance further. So you will find that from E1 you get E2, so you have V2 is E2 minus I2 into R2 plus J XL2. Okay, and this V2 is this is the load. So whenever you load this, so now we have got a fairly realistic model of a single phase transformer. So, pardon? I0 is this. That is sum of IC and IM. This is IC and this is IM. This sum is there. So we now is it clear? Yeah, pardon? Okay, so this is the I1 dash, that is the current, and I1 dash is, you have written here I1 dash N1 is equal to I2 N2. Because that MMF balance will still be continued in ideal case.
So if there is no load in the secondary, sir,
yeah.
so the only losses we have to account for are in the primary one.
Yeah. So when there is no load, the test you are conducting in the laboratory on transformer, you conduct one test called a no load test, in which when no load means I2 is 0, so you will say whatever power goes in only for the core loss. Okay, but whenever you do a short circuit here, means you are operating at low flux, so normally core loss is neglected. So the whole thing is more or less the current drawn is to account for the resistances in primary and secondary. So copper losses. So that is how you have this.
So please read the four short circuit as well.
Pardon?
So could you please repeat this?
Yeah, when you do a short circuit here, so when you do a short circuit in the secondary, what is the mutual flux? Is 0. Isn't it? Because the secondary will draw such a current to oppose all the primary MMF. Okay, so that there is, ideally it is a low flux. So when the flux is 0 in the core loss is 0 or negligible. So therefore this whole parallel branch is ineffective. It's almost like IC is 0 and IM is 0. Okay. Therefore whatever the power drawn from the mains will go for the primary copper loss and the secondary copper loss, because both the primary and secondary are drawing the rated currents. Usually you conduct the short circuit test at rated current and open circuit test at rated voltage.
So why we take less voltage when we do this short circuit?
No, when you do a short circuit, you have to operate at rated current. If you increase the voltage, current will increase. So you want to operate at rated current. Okay? You don't want to operate beyond rated current. Okay?
Excuse me, sir.
Yes.
So if there was no input and output binding resistance, and if we conducted a short circuit test,
Yeah.
then how much current would be drawn from
Ideally, it is not practically. It is not possible. You know, any wire has a resistance. Okay. So ideally, if you say there is a 0 resistance, then you must apply 0 voltage. Okay, and still it will draw a current. No, 0 resistance is superconductor. Okay. So that's what it is. So I think we will close here, and we will give a little more explanation to this equivalent circuit in the next class. Okay.